All right, today we're going to talk about verifying inverse functions, and this is similar to what we did when we were just finding an inverse function graph. I am going to talk to you about the formal way to do this. What they're asking you to do, what they're telling us here, is that if I were to make a composition of functions, put one function in the other, I would always end up with x. So here's a real simple example of that. If f of x is x squared, then g of x is the square root of x. And I did f of g of x. That means I replaced g of x here with square root of x. This notation means I would put square root of x in here, and I would have square root of x squared, which is just x. So that is what they're telling you here. If they're inverses and you do the composite, you would always get x. And you are welcome to do that, but what I'm going to do for our lesson today anyway is just have us practice switching x and y and finding the other equation to verify, because I feel like we need a little more practice with that, and then we may go back and do the composition. So here's what I'd like for you to do. Just like we did in the notes when we were finding inverse equations, we're going to switch x and y. So we have x equals the square root of y plus 2, and we're going to solve that. So to solve this for y, I need to get rid of this square root sign. So I'm going to square both sides, and I have x squared equals y plus 2. Then I would subtract 2 from both sides, and I'd have x squared minus 2 equals y, or y equals x squared minus 2, which is the other equation. So yes, these are inverses. So for today, that's all we're doing. Switch out, and you can choose either equation. It doesn't matter which one you choose to switch x and y. So on this next one, since this equation has 2 x's that would become 2 y's, you may want to choose this one to solve. So I think I'm going to use this one and see if I get this. So I'm going to switch this out for x and y. So x equals 1 over y plus 1. I multiply both sides by the denominator. And over here they just divide out. So I have xy plus x equals 1. So I'm going to subtract x because I'm trying to get y by itself. So 1 minus x, and then I would divide by x, and y equals 1 minus x over x. Well, that is not the same. This one is 1 plus, this one is 1 minus. So unless I made a mistake, no, these are not inverses. So you can choose either equation and see if you get the other. So let's do one more. Again, I'm going to do this one this time and show you how to do one that does have double variables. So it is a little more complicated. You have an extra step, I believe. But we're just going to switch this for x and both of these for y. So x equals y minus 1 over y. Multiply both sides by the denominator. So we have xy equals y minus 1. We have to get the y's on the same side. So we have xy minus y equals negative 1. But to solve this, I have to factor, and that's the step that a lot of people forget. I have to factor out the y. So when I factor out the y, I have an x minus 1, and that is what I'm going to divide by. So I have y equals negative 1 over x minus 1. Now, is that the same as this? Well, it doesn't look like it, but what if I multiply by negative 1 over negative 1? Then I get positive 1 over negative x plus 1, or positive 1 over 1 minus x. So yes, these are the same. And the way that you can find that out, when you see something like this and they don't look the same, check to see if every single sign is the opposite. Here one was positive, here it's negative. Here one was positive and it's negative. Here x was negative and here's positive. So everything had the opposite sign. So therefore we can multiply by negative 1 and they are the same. So for today on verifying inverses, all I want you to do is pick one of the equations, switch x and y, and see if you get the other equation to determine whether or not they are inverses.